Sure. Okay, so hello everyone. Thank you so much for joining. It is our great pleasure to host Nick Kaaz today. Thank you so much for coming and visiting us. And just as a reminder, Nick will be here until tomorrow. So please feel free to sign up using the speaker schedule. So Nick is a theoretical astrophysicist working broadly on black hole accretion flows. He finished his PhD in 2025 at Northwestern University under the supervision of Alexander Tchaikovsky. In the fall of 2025, Nick moved to Princeton University as a postdoctoral fellow, jointly affiliated at the Princeton Center for Theoretical Sciences and the Princeton Gravity Initiative. So the floor is yours. Take it away. And when you are like 25 minutes into your talk, I'm gonna make a sign. But yeah, thank you.
Okay, sounds good. Thank you everybody for having me and for inviting me to come talk today. So yeah, right. Like you mentioned, I work on different topics in black hole accretion flows. And an aspect of my work that I want to focus on today is warped and tilted accretion disks around supermassive black holes, where today I'm going to be specifically focusing on connection to observations of extreme variability in active galactic nuclei, such as changing look AGN. So I understand that there's not a second talk today, so I'm going to take advantage of that and just take my time a little bit more. So I prepared a 20-minute talk, but like people have questions, feel free to interrupt me at any time. But yeah, with that being said, let me get started. So first, I just want to motivate some of my work a little bit by asking a motivating question, which is, when AGN are born, are their accretion disks misaligned with respect to the black hole spin axis? Because if they are, a lot of interesting things can happen. Specifically, the accretion disk can become warped. All warped means is that the orientation of the accretion disk varies with distance from the black hole. And I'll explain the physics of why that is and why that's interesting in a moment. And so the short answer is that we think that yes, indeed, often AGN may be born misaligned, where some of our best evidence of this observationally is if in nature we observe sometimes megamasers from the outer parts of AGN disks, specifically subparsec to parsec scales, that trace the kinematics and indeed show that both the system is warped even on those scales and is misaligned with an orientation that is not usually correlated with the galactic plane. If you think about, if you measure the positions of relativistic jets in these systems, which are of course launched by the central engine, you effectively see the same thing, that the jet, which is powered at small scales, also develops large misalignments. So observationally, we have evidence that this should indeed be common. And now we actually have evidence from simulations as well. So on the galaxy end, there's been a lot of work recently on trying to fuel AGN from closer to first principles. So this is a plot from Daniel Angles Alcazar's paper from a handful of years ago, where he was looking at periodic fueling of an AGN, looking from quasar phase to quasar phase, and generally found that the angular momentum of the inflowing gas had a wide distribution of orientations, suggesting that event to event should be misaligned. So since we have both observational and theoretical evidence for this, let's think a little bit more about the physics of why this is interesting. So when black holes rotate, they literally twist up the surrounding space-time. So if you have any test particle orbits that are misaligned with respect to the black hole spin axis, they will begin precessing at a rate that's a really strong function of distance from the black hole. These are called This is called lens-Turing precession. You can see it in this cartoon. And the question is then, what happens to a disk? Because those are not test particles, those are fluid orbits. So if you just had lens-Turing precession, all of the fluid orbits would essentially precess at their own rate, and the entire accretion disk would shred apart. But of course, these are fluid, right? They have hydrodynamic stresses, they have magnetic fields, they have turbulence. So they want to redistribute this angular momentum. And as I mentioned, the broad result is that the accretion disk becomes warped. Again, just meaning its orientation changes as a function of distance. But this can change the physics of the system really, really dramatically. So then one of the questions that you want to answer is, what is the long time evolution of such configuration? And so people have thought about this since the 70s, and the classical expectation is something called Bardeen-Peterson alignment. What happens here is that a thin tilted accretion disk gradually aligns in its inner regions with the black hole spin axis, and nothing too interesting happens. If you believed that the story ended there, then there wouldn't be too much more interesting to talk about. But there's different things that happen, and there's issues with this. So firstly, we've at least one general relativistic magnetohydrodynamic simulation simulating this. And first, we find that the alignment radius predicted by theory is wrong, and instead this aligns much, much closer to the black hole spin than you would naively predict, suggesting that even in this kind of more simple regime of small tilts, we're not getting things quite right. And secondly, there's a bunch of missing effects. So first of all, smaller tilt angles can't be described by linear theory, so perhaps something else happens. We know that things like self-irradiation may actually grow existing warps, but we don't really understand how that happens. And there's other effects where people have explored somewhat in the literature that they don't understand, such as, there's been theoretical evidence that nuclear star clusters can excite time-dependent warps and disrupt this picture. So what our group has found, and other groups have found in numerical simulations, is that when you go to higher tilt angles, something else entirely happens. Specifically, the black hole spin ends up winning. And the accretion disk, instead of just aligning, gets torn apart into multiple individually precessing subdisks, as you can see in some of these cartoons and various simulations that I'm showing here. This is really interesting because, of course, then the dynamics are completely different, and you can imagine that the observed variability would also be extremely different in these systems. Okay, so now I'm going to show you a movie. And so this is an extremely high resolution simulation that's actually kind of old now. So this was performed by Matthew Liska in 2019. So this is a thin tilted accretion disk with the black hole spin on the vertical axis, and I'm showing you gas density. And so you can see a lot of these effects that I just described. The entire structure becomes warped, and the inner regions periodically tear off from the outer regions. They differentially precess a little bit, but then they get rapidly consumed, leaving a hole in the middle of the system that then has to get replenished. So this is really hard to simulate, both thin accretion disks in general and large tilt angles. So I said this simulation is like 6 or 7 years old now. I think it's still the most expensive accretion disk simulation that's ever been performed. So I just want to put in perspective that it's really not feasible to do this very often, okay? And so there's a lot of interesting things here to talk about, but today I'm going to be talking about some of my work on synthetic observations. So I want to think a little bit about the extreme variability that happens here. Okay, so this is an old plot that I made a few years ago, where I did something really simple, which is that I just took a projected image of density squared in these simulations with the timescales rescaled for a 10 to the 8 solar mass black hole. And so you can see in the top left that we are at the beginning of a tearing cycle. And then as we moved to the top right, the inner disk is depleted, leaving a hole in the middle of the system. And in the bottom panel, the inner regions replenish and the tearing cycle occurs again. And then if I make a really crude measure of emission, just integrating the dissipation leaving the system during this phase, I get this plot to the right here. So each of these pink vertical lines correspond to the panels to the left. And so you can see at the beginning of the tearing cycle, we have a peak in emission. As it depletes, as you delete the inner disk, you have a trough. And as you replenish, you rise up by about a factor of 30. This is really dramatic variability, order of magnitude variability, and it happens within about 2 years. This is a really, really short time scale for an accretion disk. Usually you would expect a standard viscous time scale to restructure the system, to refill those inner regions on the time scale of centuries. And what's really interesting about that is if you turn to changing look active galactic nuclei, these are essentially sources that we don't really understand that undergo order of magnitude variations of luminosity consistent with something dramatic happening to the inner disk, and they evolve on timescales of months to years. And that is indeed one of the hardest things about explaining them, is because those are fast timescales. So now I'll briefly mention that there's a lot of interesting physics here that determine the inflow rate in these systems. This is something that I've worked on in the past, where you generically find that strongly warped accretion disks are much more efficient at driving inflow than unwarped systems. This is not something that I have time to talk about in detail today, but if you're interested, feel free to ask me. Okay. So after seeing this, what I wanted to do was take this idea a little bit more seriously and see if there is a connection between disk tearing and changing look active galactic nuclei. So I sought out to produce synthetic observations of the simulation that I just described here. And first, I want to give a little bit of a quick primer on what the broadline region is and why that's related to changing look AGN, because this is related to the synthetic observations I made. So when we look at SEDs of luminous AGN, we see a variety of different features. And one of them is that we often see a broadline region. So this can be in the optical, for instance, we see emission lines that are broadened somehow that seem to be consistent with photoionization from the central engine. And so we don't really know exactly what is driving this region, but observationally we can constrain what it is. So what people usually think is that at, say, 10 to the 3 to 10 to the 4 gravitational radii, there is perhaps some tenuous optically thin region of connected clouds that are rotating perhaps in a circle or in an outflow geometry. And these are photoionized by the central engine. And when they are photoionized, they become hot and they re-emit, they re-radiate and produce emission lines, okay? And so people don't always see broad emission lines. And so people classically sorted active galactic nuclei by whether or not these broad emission lines are present. So you can see here in type 1 AGN, they are apparent, type 2, they are not. And so what people have done in the past is that they attribute this difference, whether or not you see these lines, to viewing angle effects. If you see it more than edge on, you don't see these clouds and you don't see these broad emission lines. But if you look at it more than face on, more like face on, then the broad emission lines become more apparent. Okay, so this is why changing look AGN were weird to people, because it was, if you looked at a source 1 year, you would see these really broad emission lines. And then if you looked at it a year later, those emission lines would be totally gone. Clearly, your viewing angle is not changing, so something else must be happening. And as I mentioned earlier, the reason the broad emission lines are there at all is because you're photoionizing this gas from the central engine. So what people think is that if you turn the central engine off, you have to turn these broad emission lines off too. And so that's the connection, okay? Okay, so getting back to the simulation, this we evolved this system on scales of 100 gravitational radii, about 100 times the size of the event horizon, okay? The broadline region is at much larger radii, so we don't simulate it. Instead, we make assumptions and I produced a synthetic broadline region. And so this is kind of a cartoon representation of it, where I assume a torus-like geometry, and I use a covering fraction, density, thickness, etc., that are consistent with what people infer observationally. And so, right, so I want to make synthetic observations of both the broad emission lines and the continuum. So first, I wanted to do ray tracing, which I did the simplest possible version of this, where the idea is I have some camera pointing at my system with some image plane, and I ray trace backwards in time. I ray trace the trajectories of the radiation down to wherever the photosphere is. So for emission properties, I'm just doing the simplest thing where I'm assuming everything is just thermal. Okay, so I ray trace the light, and so for example, from the line of sight, I get the continuum emission. The second thing I did was I distributed cameras throughout the broad line region and ray traced the light to every single segment of this structure. The idea here is that gives me the photoionizing flux that's incident upon it. So, right, in this pipeline, once I have the radiation that's hitting every part of the broad line region, I hand off my calculation to the software Cloudy. If you're unfamiliar, this is a software that takes incident radiation upon some gas, upon some cloud, and determines its photoionization equilibrium. So it allows me to predict how the emission lines are re-radiated. And as I mentioned, this structure is rotating, which gives you Doppler shifts, which causes all the lines to be broadened. So for the optical emission lines, you end up getting something like this. Broad H alpha, H beta lines, for instance, that have some structure that is determined by what's happening over here. Okay? Okay, so this plot is giving you some of the broad takeaways. So this is late in the evolution of the system in a time window of about 2 years. So on the top here, this is the volumetric luminosity. And here is the re-radiated line luminosities. And the broad message is you see various peaks that happen to be driven by these tearing cycles that undergo indeed this order of magnitude variability on these timescales of months to years. And then if you turn to the broad lines, they undergo the exact same sort of variability. They vary by about an order of magnitude. So if I show you the optical spectra at 3 snapshots, you see something like this. So this is at the peak of the emission. So you get very clear broad emission lines. Then it falls into quiescence, and the emission lines basically disappear. And in the third panel, we have a shorter period of activity. So you have broad lines, but they're weaker. And so this is exciting because that means that we've simulated here a bona fide changing look AGN. And remember that we don't really have good theories that actually explain what these sources are. So it's really promising that this works at all. It's also not necessarily that surprising. We know the system is changing dramatically. So I think what is more interesting to do, though, is to say, okay, if this exists in nature, it can produce changing look AGN. Can we actually observationally diagnose that? Can we look at a system and actually determine that disk tearing is powering this kind of variability? And the exciting thing is that I think we can. So what I want to do is go back to this volumetric luminosity and focus on one peak here. So superimposed upon the peak down here, you can see a few epicycles. This dotted line in the back is the mass accretion rate. So the luminosity largely traces the mass accretion rate, but the mass accretion rate doesn't show these same epicycles. So what's happening here exactly? And it becomes clear if you look at the ray traced images. At the peak of these tearing events, the inner disk is actively precessing. And so you can think about it as a lighthouse that's moving in and out of your line of sight, adding to the variability. Now, this is a violent phase of evolution. You don't get very many coherent precession cycles, so you can only get a few, but they're there. And the interesting thing is if you look at the exact same period in the line luminosities, you don't see this variability at all. But this actually makes a lot of sense if you think about the geometry. This is a line of sky, this is a geometric effect. The lighthouse is avoiding your line of sight. But the broadline region should be basically axisymmetric. So just because the lighthouse moves, it's now just shining on a different part of the broadline region. So it's still seeing the same amount of flux, so the same amount of re-radiated luminosity, or the re-radiated light shouldn't change too much. But that doesn't mean nothing changes. Because what we have to remember is that the reason that these lines are broad is because this structure is rotating. And so different parts of the broadline region will contribute either to the blue shifted or the red shifted side. So you can imagine that if this precessing inner disk is shining more on the blue shifted side, if the line was previously symmetric, it should become strongly asymmetric on the blue shifted side. So motivated by this, I went looking for these asymmetries. So this is kind of a messy plot, but here is the H alpha line flux. And so I'm looking at it as a function of time here. And this is the frequency offset from the line center in terms of velocity. And you can see that there's a lot happening here. The overall strength of the line, this is in log space, right, is changing pretty dramatically. And there's some asymmetry. But it's hard to really infer exactly what's happening. So to look for the changes in asymmetry, I also wanted to look at the residuals. So I basically subtract the line, the spectrum off of some moving average, and I get a plot like this. So the right is the blue shifted side, the left is the red shifted side, and green is showing you excess emission, blue is showing you a deficit. So if there's green on the blue shifted side, that means there's an excess of blue shifted emission. Okay. So let's go back to this event, this height of the tearing cycle where the disk is precessing, and think about what's happening here. So this is the line that's clearly evolving and its symmetry properties are changing. And each of these pink horizontal lines correspond to the panels to the right. And if we look at the residuals, we can see that the green starts on the blue shifted side. So there's a blue shifted excess. And then as the disk precesses, that excess moves to the left side. And once the precession cycle completes during this event, it switches to a blue shifted excess again. So this is cool because this is a signal that you could go looking for in nature if you have high enough cadence spectroscopy. And what's cool is that this is something that people have actually reported very recently in the literature. So this is a source from an AGN storm campaign where they describe, this is the same kind of plot I just showed you, it's just actual data, so it's a little harder to see. But they report basically a bar purple pattern. It's kind of hard to see, but you can see these patterns are moving from relative blue shift to relative red shifts. I don't know how obvious this actually is, but the point is it's evolving, and then they attribute it to some kind of precession. For this specific event, the numbers exactly aren't the same as what we find in the simulation. But again, as I mentioned, simulation is just one data point. There's likely a range of dependence on disk thickness, spin, etc. If this indeed happens in nature. And right, if we look at changing look AGN in general, people are also reporting evolutions in the asymmetries of the broadline region over longer timescales as well. So this is an example for a repeat changing look AGN. And so an important part of this whole story is that these tearing cycles necessarily repeat. So this should be specifically for repeating changing look AGN. How am I doing on time?
You have about 5 minutes.
Oh, okay. So there's one other cool thing that I wanted to point out that's different from that observational diagnostic, which is if we look in part of the band luminosity, so we're looking at these colors are tracing in our disk radii of like 5 to 10 gravitational radii, you see these little oscillations. And it turns out that we're actually seeing a quasi-periodic oscillation. So if I take a PSD of the light during that phase that I just highlighted here, you end up getting a signal that looks something like this. This is an extremely prominent QPO that's occurring basically twice per day. So what's driving this? This is interesting, right? And so this has been studied before by a paper by Jabwa, where it turns out that when the disk tears, it can be perturbed, unsurprisingly. It's a really violent evolution, and it actually undergoes axisymmetric radial oscillations. So here, what you can see is this is the density in the disk during this QPO. So here's where the disk tears, the density is basically depleted. This would be the outer parts of the accretion disk. And here is the inner disk that's kind of centered around some radii between 10 and 15 Rg. And so this is the centroid radius. And so I'm showing you this detail of where this inner disk is centered, because if we look exactly where this QPO is, this gray shaded region is showing you the value of the radial epicyclic frequency at this radius. So this should be the frequency that these radial epicyclic, these radial axisymmetric oscillations operate at. And so, you know, the fact that it's really, really coincident with this radial epicyclic frequency is really good evidence that this is indeed the mechanism that's happening here. And so I'll also mention that this is a paper about changing look AGN. This exact thing should happen in X-ray binaries, and this is the same frequency as, and this would correspond in those systems to high frequency QPOs. So I'm just mentioning that if this is something that anybody's interested in, it's something to think about. Okay, I guess that's my summary slide. So I'll wrap up and take questions. Thank you.
So when people are thinking, oh, sorry, can I take this privilege? Thank you. So I have a question. So when you're doing this ray tracing, what's your assumption about the torus? Because like obviously
Like the broadline region torus?
Yes,
Yep.
like the obscuring material that, you know, people return to when they're trying to explain changing look AGN and the changes in spectrum type just based on obscuration arguments. So because you have said that you assume a typical covering fraction, but I mean, we suspect that, you know, tori are not these donuts that you showed, but so.
Yeah, well, okay, so I'll say a few things. One, because you talked about obscuration, and I know people talk about changing look AGN, either driven by obscuration or driven by genuine changes in the state of the accretion disk. So I'm talking about the latter. And so the assumption here is that this is elevated, this is some structure elevated 45 degrees above the accretion disk far away. So I basically take the outer edge of my disk and I extrapolate it. So I pretend it maps onto a much larger AGN structure and I elevate it at 45 degrees. And I assume that it has some, again, it's a very smooth structure. And so I assume that it has some number density and some column density. I don't want to tell you because I feel like I'm going to get the order. I'm going to misremember exactly what number it is when it's in the paper. And so the covering factor, I think it ends up being around like 10 to 15% or something like that. I'm not 100% sure. But my understanding is that now that we have like gravity observations of you know resolved broadline regions, they do favor torus-like geometries in some cases and outflow geometries in other cases. I think if you chose a different geometry, it's really hard to avoid something like this occurring, but that's why I chose a torus-like geometry. Did I get your question?
Yeah,
okay.
Absolutely. Thank you.
I have like a practical question. We have a source, the paper was published last year.
Okay.
NGC 3259. It's a low mass black hole, like 300,000 solar masses. And it shows H alpha variability at a factor of 20.
Oh, wow.
But no, over 15 years. Okay, up and down. But no variability in the continuum flux.
Okay.
Moreover, it shows significant absorption in X-ray.
Mhm.
Again, but with CH alpha, we barely see H beta, so H alpha to H beta is pretty high. I'm not sure whether it's extinction, probably it is. So our interpretation was that we basically couldn't see the central source because of the geometry of the torus, but that we could see the broad line, and that's why we don't see the continuum variation. But we thought that we were dealing with an asymmetric broad light region because we kind of saw, like, we attributed the symmetry of the light going blue wing to red wing to this kind of, if you have, like, I don't know, like an egg-shaped thing that you rotate, sometimes you would have a similar effect. So do you think that in low mass black holes, this mechanism can go?
So, well, short answer, yes, but so a few things. So in this specific simulation, this is not explicitly radiative, and what that means is that as far as like the code is concerned, n=1.
Oh yes, our Eddington rate is sort of a few percent.
Yeah, so that's the correct Eddington rate. So it's really not something that we expect to depend on the black hole mass. Like, it should be able to happen in whatever black hole mass you have, as long as the Eddington ratio is kind of in the right spot. But the one thing that I will say is that the timescales, like pretty much any variability, are linear with the black hole mass. So if this is months to years for a 10 to the 8 solar mass black hole, it should be a factor of 100 shorter for your system. So I think if it's changing on years, I think that that's probably too long for this to be right. But the other thing that I'll mention is that there's a whole world of warps and global distortions of accretion disks. This is very close to horizon scales. There's people who have looked at warps on much larger scales. So you can imagine geometries easily where other things drive their warp, like nuclear star clusters, for instance, that change it such that you can only see part of the broadband region while you're missing the central engine. So I think that there's connections there, but specifically this mechanism, even though I like when it explains things, the numbers seem like
so the time scales would not work.
I think the time scale issue, yeah. I mean, the challenge in general is just like, to really determine this, you need really like high cadence optical spectroscopy.
How high?
Well, so here the source happens, the variability happens in the time scale of a week for a 10 to the 8 solar mass black hole. So I don't know how, like, AGN storm has that sometimes, but I think it's still really rare. Learning more about observations.
We have one question on Zoom. So if the person wants to unmute themselves.
Hi, Nick. It's Angelo. Great talk. Given that most AGN are not changing look, as far as we know, do you think that means that extreme misalignments are not very common in the universe, and that could have some implications for spin evolution? What are your thoughts on that?
Well, spin evolution is a whole other question.
Yeah.
So I'll say, so caveats physically, right? Usually when you do a GMHD simulation, what you expect is some gradual steady state. The inner regions gradually converge to mass accretion rate being constant. You don't see this kind of cyclic behavior, et cetera, et cetera, et cetera. In the lifespan of these, like, even these are very long duration simulations for a torn accretion disk, for a GMHD. In these timescales, the variability seems to repeat. This is still far shorter than like a quasar duty cycle or a quasar, or the cycle of a quasar episode. So it's not obvious yet if you turn a misaligned AGN on for 1 million years, if it'll just keep doing this forever. Like, in fact, I think that it would actually, even though I would love that, it seems like it's hard to imagine that it actually works that way.
Sure.
In addition to that, the black hole torques the gas also torques the black hole. So eventually, just from gravitational torques, the black hole spin and the disk will align. The time scale of that depends sensitively on warped accretion disk physics that we still don't understand yet. So whether that's 1 million years or 100 million years, I think it's still open. But but I don't think you can make any strong statements about the distribution of misalignments based on how common changing look AGN are.
Thanks a lot.
Also, and let me be clear though, there's probably multiple mechanisms that explain these sources. There's a lot of things that can happen. So I'm not trying to say that this explains all of them. Just comment.
Peter?
How about tidal disruption events? Those would be some of the most ideal scenarios for you.
Yeah, tidal disruption events are wonderful because you're like, they have to have random angles. The caveat is that most of those systems are super Eddington. So super Eddington's gonna be a lot thicker. So this is what I was mentioning before. The reason this depends so sensitively on Eddington ratio is this happens the most easily in thin accretion disks. If you're going super Eddington, it's going to transport the warp differently. It's a lot harder to tear. It probably wouldn't happen there. But I would say the interesting connection is partial tidal disruption events, because people talk about these actually being quite common. So if you normally think tidal disruption events are super Eddington, but partial tidal disruption events, you have a much smaller mass accretion rate, in those systems, something else interesting can happen.
Yeah, I just want to add that there are some sources in which there are claims of line steering precession.
Yeah.
So that is exactly this scenario.
And I love lens turning precession. I like when it's correct, but I think sometimes it gets attributed too easily to sources. But yeah.
Okay, any final questions for Nick online or in person? Great topic. I'm wondering about the overall mass accretion onto a black hole, with a warp disk and a standard one. Is there significantly more mass accreted?
So what I'll say, this is something that I mentioned briefly, but I haven't really talked about today, is that there's a lot of things that change about how inflow happens at strong warps that make it, you end up getting inflow velocities that are a lot higher than a standard alpha disk, because standard alpha disk might suggest that the radial velocity is like a millionth of Keplerian, and here it might be like 1,000th instead. That being said, it doesn't necessarily mean that your overall mass evolution is changing, because ultimately what's setting the mass reservoir is something happening much farther. So you can give the AGN the exact same amount of mass, and whatever's happening at the inner region will just change how fast you eat that. But in terms of cosmological evolution of them, I don't think it would change dramatically. Yeah.
Okay, any final questions? Okay, no, so let's thank Nick again. So see you next week. Yeah, thanks a lot.